So hello everyone. So welcome to the new semester's Rogers Efficient AI seminar. And today is the talk for our first talk. And we're glad that we have Professor Yiyu from the University of the Notre Dame to give us this talk. Professor Shi is currently the full professor in the Department of the Computer Science and Engineering. And he is also a visiting scientist at the Boston Children's Hospital. He received his bachelor degree from the Tsinghua University and the master PhD degree from the University of the California, Los Angeles. His current research interest focuses on the hardware intelligence, biomedical applications. And he has won a lot of the awards and the best paper nominations. He received the IBM Invention Achievement Award, Japan Society of the Promotion of Science Faculty Invitation Fellowships, IEEE Career Award, and many awards there. And he is also Facebook Research Awards, ETC VSI Mid-Career Research Achievement Award. And he is the deputy editor-in-chief of the IEEE VSI CAS newsletter, and also the associate editor of the various IEEE and ACM journals. So now let's welcome Professor Shi to give this talk, Hardware and Software Co-Design for the Deep Learning Accelerators.
Okay, well, thank you for the kind introduction, Bo, and well, good morning, everyone. I'm very happy to have the chance to share with you some of our recent research directions. So I'll first start with usually I'll start with a, kind of a brief introduction about the AI, but I guess everyone here knows AI very well. So AI has been showing great potential in a number of applications, including disease diagnosis, which is the application that my group has been looking at. But beyond that, there's been like gameplay, autonomous driving, there's real-time translation, there are lots of applications where we've seen AI, showing the great potential, right, with the superior performance. But the biggest problem we always have, when we want to deploy AI to a particular task, is the design of a neural network. Assuming that everyone is using the deep learning, the deep neural network, then the problem is, or the question is, what kind of neural network should we use for this particular task? Now, in the early days, we could just manually craft those neural networks like AlexNet, VGG, ResNet, different kinds of neural networks. They were mostly invented manually, right? We tried different configurations, we tried different tricks, and see how they adapt to different tasks we have, right? For example, the ImageNet. Now, the potential issue with this kind of approach is the scalability. When we wanted to deploy AI to a large number of applications like IoT, where each different application or each domain can have a different data distribution, which means that the best neural network architecture might be different. Usually, the design of a neural network for a particular domain or a particular data distribution requires domain knowledge, and also a lot of time and effort. So just to give you one example, right? We're working with doctors to try to apply neural network for different kinds of disease diagnosis. We actually found that for different type of disease, actually the best neural network will be different. And sometimes they differ a lot in terms of the the number of layers needed, in terms of whether we should use skip connection or not. They're different. So not to mention that we have a lot of applications beyond the medicine area, right? So it takes a lot of effort to find the best neural architecture, and it's not possible to manually design a specific architecture for each application manually if we want to deploy AI to a large number of domains. So then actually we had the idea of neural architecture search, which was actually brought up about 5 or 6 years ago. The main idea of NAS, just to give you a brief background, was a kind of like an automatic optimizer that learns to find the best architecture for a particular data set. There are lots of the different techniques for neural architecture search or NAS. The earlier ones, or the ones that are more or less popular, was the based on the reinforcement learning framework, where you have a controller, an RNN, that learns to generate the best neural architecture in terms of, for example, accuracy. And then the RNN will each time sample an architecture with a probability P. Then we train this neural network based on the data set or a proxy of the target data set to get the accuracy A. And then we use this accuracy to reward or penalize the this performance of the controller so that it learns to generate better and better neural architectures. So that's the main idea. And of course, there are different variations of it that improves the performance. I think there's some kind of echo. Not sure if it's my problem or let's see. Okay. So this is the main idea of it, and actually and it works pretty well. But there is one implicit assumption, is that there's no constraint or no limit on the hardware resource you can use, right? And of course, if you can deploy your network on the cloud, there's no problem. Usually, you have enough computing power. The network can be large. You can have sufficient computing power to do whatever computation you need. But let's say if you want to put it on a resource constrained environment, like an edge device, smartphones, right? If that's the case, then we can potentially have a problem. So the neural network identified by this NAS process, the process right here, it may be huge, because we never constrain the size or the capacity of the network, right? It can be huge. Now, if you want to put this huge network on a resource constrained device, you might have to do some kind of pruning, truncation, quantization, which may limit the performance or degrade the performance in terms of speed, in terms of accuracy. So it may or may not meet the target spec, depending on how resource constrained the hardware platform is, right? And so we're looking into this problem back in 2018. We did a survey that was published in Nature Electronics. We look at the size and the performance of the computing power needed by the leading neural networks, and also the potential capacity of the hardware that can support these neural networks. So there are a few interesting findings that we got. The first thing is, the figure right here shows you, in terms of the performance, the x-axis is the top 5 error on ImageNet, and the y-axis is the number of operations needed by these neural networks. We'll look at 2 different sets of networks. One is actually that comes from academia, more or less, well, I would say less structural optimized. And the second set is the ones from academia, with the structural optimization. So they more or less are aware that we need to make the network compact, make them small. So the one is in blue without structural optimization. The ones in green are the networks with structural optimization. But either way, you can see that the number of operations actually increased exponentially with the top 5 error decrease, because this is in the log scale. But on the other hand, we also looked into most of the state-of-the-art platforms, like in terms of the year that they came into, they become available. The y-axis being the performance density in terms of the gigaops per second per square millimeter. So that's per unit area per unit time, how many operations can be supported by these different, either the GPU, we try the GPU, we try the ASIC, we try the FPGA, so different hardware solutions. And it doesn't matter which one we're looking at. There is some slight increase in terms of the performance density, but more or less they are flat. At least they are not increasing at the same pace with our size of the or with our number of operations needed by the neural networks. So that gap is increasing. Actually, it's getting bigger and bigger. So we either have to make the networks, actually allow them to run longer, or we have to make the chips bigger in order to support this increase in the number of operations by the neural network. And the same thing holds for in terms of the memory capacity. So this figure right here shows in order to get the error down, the top 5 error down, what's the number of parameters or the size of the neural network. Again, you can see an increase. This time it's less obvious, it's still getting bigger. But at the same time, you can see that the energy efficiency in terms of the how many bits can be moved within per unit energy, right? In terms of a nanojoule. And you can see that again, it's increasing, but in the past 4 or 5 years, it more or less remains flat in terms of this energy efficiency of a memory. And which means if we wanted to keep supporting the state-of-the-art neural networks, if we don't do anything else, we just deploy them as is, then you need to pay the cost, in terms of the energy. They need to use higher and higher energy in order to support the operation. So in light of that, there was some of the works that start to look at we call the hardware-aware neural architecture search. The main framework remains the same, which you've seen already for the NAS. And there was an added kind of branch out here based on the sampled neural network from the RN. In addition to looking at the accuracy, you also try to predict what's the hardware efficiency, like the energy, the delay, right? Whatever hardware performance you want to look at. We look at the hardware efficiency, E, on a fixed hardware, like a mobile phone, or like an FPGA, whatever hardware platform you have. And then you'll basically penalize or reward this controller based on both the accuracy and the efficiency. So this way we're taking the hardware performance into consideration. So there's no surprise towards the end, like when you are done with this NAS, when you get the actual optimal network, you know that it's optimized for the particular hardware. So you don't get any surprise towards the end. Right? So it works, and it works for particular fixed hardware because you need to know what's the hardware, right? You need to know the hardware platform in order to predict the efficiency. But what if you have it's not a fixed hardware? What if you have the freedom to design the hardware, right? And so this is what we are actually interested in. And because there are many different platforms that actually allow you to customize the hardware design. So for one example, FPGA, you can actually program it in different ways. You can have different scheduler, you can have different mapping algorithms, you can have different tiling. Each will give you a different performance, different design. So how, right? What if it's not fixed? And now in addition, if let's say if we talk about ASIC, we talk about a fully customized design, then you can have the entire freedom of, in the whole design space. You can decide everything from scratch. So that makes the problem even more complicated, right? How can we deal with this kind of hardware platform? So this is our basic idea, why we started to look into this kind of problem. So we have the pure neural architecture search. We know that we eventually want to implement this neural architecture on the hardware, which can potentially be programmable like an FPGA. And there is actually a missing link between identifying the best NAS and try to implement them in a programmable or flexible hardware space. So if we look at the timeline of these different NAS frameworks that I've already briefly covered, earlier, from 2012 to 2016, 15, 16, most of the networks are human invented, like I mentioned. And then starting from late 2016, there was the first work, the reinforcement learning based NAS. Following and afterwards, there are lots of other like the differentiable NAS. Or there are other types of NAS. There is like a one-shot NAS to improve the performance in that direction, but they are purely and automatically exploring the neural architecture space. Then starting from 2018, there was a neural hardware-aware NAS, which again, there was work from Google, MIT, Facebook, Berkeley. They were looking at how to design and how to identify a neural architecture for fixed hardware, like a smartphone, right, or a given design. And we actually were the first to identify the design and the identification of a best neural architecture if the hardware is also flexible. So that was published in DAC 2019. We named our framework as FNAS. That was the first work for the neural architecture space and the hardware design space co-exploration. And after that, this was the work for FPGA, and I'll explain that in great detail later. And afterwards, we also tried we continue to explore along the philosophy of co-design. We tried different other platforms like ASIC. We tried the network on chip. We explored all the possible hardware platforms that are flexible, and we have one framework for each, which I'll also briefly explain later in this talk. All right, so as I mentioned, we start with FPGA. The reason for that being, number one, FPGA is one of the most widely used DN accelerators today with flexible programming capability. So for example, on the cloud, right, we have the Amazon, they have the FPGA-based cloud, Xilinx, they provide FPGA accelerator. There is also a Microsoft FPGA cloud as well. And then if you look at the edge computing, there are also quite a few autonomous driving companies that deploy FPGA as an accelerator on the edge. So that's why we decide, hey, maybe that's a good starting point that we can look at. So just a brief comparison of a hardware-aware NAS and our co-design framework. This figure on the left here shows what we'll get and the basic flow for a hardware-aware or FPGA-aware NAS. You've already seen this. We have a controller that samples the hyperparameter of the network. We sample the number of filters, the filter size, the stripes parameter, number of filters, all these. You have one set of these parameters for each layer. Once you have sampled these, you get into training, you get the accuracy. And then you map that to a particular CPU or GPU or whatever hardware you have. You get a latency L, and then you compute a reward based on the function of both the accuracy and the reward. And as a result, what you're going to get is a hardware-aware NAS. And as a result, you get an optimal neural architecture. That's it. This is the architecture you'll be able to apply on the fixed hardware. Now, what we actually did, and we expanded this framework, is that we have two loops. The outside loop we call the slow level or software optimization. It's the same thing. You train a sample network to get accuracy. But we also have an inner loop we call the faster loop, which I'll explain why later. But for now, it's just hardware optimization. So for the sampled neural network, we also try to optimize the hardware for that particular neural network we sampled. Then we get the latency L. And then, the rest of things remains the same. We look at the latency and we decide whether it's how we should penalize or reward the controller. And as a result, what you're going to get is not just a neural network, but also the hardware design for that particular neural network. The pair will give you the best performance. So now this framework seems to be pretty straightforward, right? You just have an out loop that remains the same. You get accuracy. You evaluate on the target data set to get accuracy. In the inner loop, you try to optimize the hardware. The problem for this is actually this inner loop where you want to optimize the performance of the hardware or the design of the hardware based on the sample neural network. It's pretty time consuming if you use any of the existing framework. Because let's say one naive solution would be, hey, let's sample a neural network, and then we try all the different potential mapping algorithms, potential scheduling and mapping scheduling algorithms on a particular FPGA, right? Let's just try all the combinations and see which one is the best. But for that, it's just not possible. Computationally, it's too expensive. Now, for reason number one, we just tried a single layer. Let's say we want to map layer 5 onto an FPGA, right? And it's a layer 5 of Alex, and it's a pretty small layer. And even for that single layer, we did a scatter plot, for different design of the FPGA. If we use different strategies, the x-axis is the computation to communication ratio, like whether there's more on the computation or it takes more time to communicate. And then the y-axis is in terms of the performance, right? In terms of gigaflops. So you can see that there is each design gives a different solution in this space. So there are too many to explore. And in addition, usually we don't just use a single FPGA to accelerate the design. You need multiple FPGAs. So that further expand the space, the potential design space, right? And finally, even if you get just a few of these potential designs, if you use a traditional performance evaluation, you go from functional spec, HDL, you want sensitivity, replace and route, and finally hardware evaluation. That's going to take a long time to evaluate a single design. So we need a much faster approach, because this is used in the loop inside a reinforcement learning, right? So we cannot afford a long time to do this. So that's why we develop a very fast and approximate, but with reasonable accuracy framework. That I'll just give you a brief explanation. Again, in the interest of time, I don't have time to go into too much detail of this. But just if you're interested, you can refer to our paper that I'll give the reference at the end of my talk. So the main idea of our framework is composed of 4 different steps. Let's say we start with an FPGA. So we know that for the given FPGAs, we have a few possible FPGA we can use, and exactly which one we should use, that's a design freedom as well. So let's say we have different FPGAs. Each one, we know the number of lookup tables, we know the number of DSPs, we know the memory capacity, we know their specs, so we can use. And we are also given a neural architecture with determined hyperparameter. Now, this is already sampled from the reinforcement learning. So this is one iteration in that reinforcement learning. So we know the neural architecture, the hyperparameters. It's from the sampling of the RNN. The first step is we wanted to decide how do we allocate the on-chip buffer in the FPGA. We want to decide the accelerator size. So how much of the, for example, lookup table we should use for the accelerator, right? For the exact computing, and how do we allocate them for the memory? And both of these design decisions are actually decided by the tiling parameter, right? So TM, TRTC, where MN and TM are the tiling parameter for the input and output. The feature maps, and TR and TC would be the channel-wise, the channel tiling parameters, so the weight tiling parameters, right? So these are the decisions we have to make. How do we cut these data into pieces for the tiling? And of course, you have multiple layers, and you also have to decide the computing parallelism. Like, for example, for the input feature map, output feature map, how do you decide the buffer? For the weight, how do you decide the size of the buffer? That decides your parallelism, right? How do you cut them? So that's the first step. We try different tiling parameters as a part of the optimization loop, and then we try to find the best one. So this is embedded in the reinforcement learning framework. And once we have that, the next step would be we try to decide. Let's say we have all the tiling parameters decided, right? Let's sample, let's say, in the reinforcement learning. Then once we have that, we can extract a high-level graph, for the computation, the dependency graph. So here's one example, like for each layer, like convolution layer 1, convolution layer 2, how these computations are how they depend on each other, so that we know which computations can be done first, which one has to wait for the previous ones to be finished. So we get this graph of dependency in terms of the computation. And this is pretty fast and automatic. You can extract this computation once the dependency, once you know what's the tiling parameters. Now, once we have this, the next step would be to do a scheduling. There are lots of available schedulers. Once you have this dependency graph, there are lots of scheduler we can use. So we basically schedule these tasks, these computations on the multiple FPGAs. For example, we know that the PE2, the processing element 2 should wait for the processing element 1 to finish these computation, and then it can kick in to start its computation. And now you can do some reuse, like the input feature map reuse, you can do the output feature reuse. So all these can be done automatically, again, based on the dependency graph. And finally, once you have that, then we can do a quick estimation of the latency by looking at the pipeline start time, including all the, this wait time, plus the actual processing time. So for this case, the actual time or the latency would be from here to here, right? So this is the latency we can get. So, and as an output, you get a tailored FPGA design, and you get the system latency based on this estimation. So this is embedded again in the entire reinforcement learning framework, so that we can search for both neural architecture and the both FPGA design at the same time. So without talking too much detail about the algorithm, let's look at the results, which I think are more interesting. We tried two FPGAs, Xilinx 7850T and 7Z020. They have different specs. We tried the data sets. We tried from the smallest MNIST to the largest ImageNet. The hardware search space, the NAS, the neural architecture search space include the number of layers. We allow the number of layers to be up to 5 for MNIST, up to 15 for ImageNet. The filter size can be selected from these candidates, and the number of filters can be selected from these candidates. This is the search space that we provided. The hardware search space, including, like I said, the channel tiling, the row tiling, and column tiling parameter, and the different schedulers we can choose from. Finally, as a hardware design target, we specify to the framework what is the maximum allowed latency in terms of millisecond. So this is the maximum time we will tolerate. Any neural network that actually takes longer than this timing spec to run or to get to for the inference, we think it's a failure. It's a failed design. Whatever it's the accuracy is, it doesn't matter. It's a failed design because it takes too long to run. And the timing spec we set 4 different sets for comparison. The tightest timing spec we set is 2 milliseconds for MNIST, and the longest we allow is 20. We set different specs for CFAR and for ImageNet. So here are the results. We first use MNIST to compare, for the hardware, right? On a different hardware, let's say the 70020, 7850T. We compare a pure NAS without considering hardware at all. And then we compare our FNAS with loose timing spec, meaning we give, for example, 20 milliseconds for it to finish. We allow the network to be relatively big, or we allow a very tight timing spec, only, for example, 2 milliseconds, which means the network has to be small in order to fit. So this is the search time, how long it takes for our framework to return the optimized solution in terms of a pair of neural architecture and hardware design. So it doesn't matter which one you look at. Basically, you can see that the tighter the timing spec is, the shorter it takes for our framework to run. And all the 3 are much faster than the pure NAS without considering the hardware. Now, this explanation actually reflects our naming of the inner framework, which is the faster loop for the hardware optimization. because our framework, from deciding the timing parameter, once you decide that, you go down all the way to the get the final latency, it's pretty fast. It's much faster than you train the sample network on a target data set, on a proxy target data set to get the accuracy. So our strategy is, once we get the latency, we do a quick test to see if that latency is bigger than the timing spec, or the maximum latency or not. If it's larger than that, this is a failed design. Then we stop the training, we kill the training, because whatever the accuracy, it will fail. So it's going to be a large penalty. So this way we can quickly prune this architecture, this candidate. And so the tighter your target, the timing spec is, the more you can quickly prune without waiting for the training to finish. So that's why we get faster and faster if you have a tighter timing spec. And in terms of the latency, what we can obtain, you can see that compared with again, the NAS without considering hardware, the tighter the timing spec you get, of course, we can meet the timing spec. So the smaller it takes for our method for the network to do the inference, right? This one's the fastest, you can see. And well, then you might be wondering, well, you can identify the best accuracy with that satisfy the timing constraint. Would that accuracy drop a lot compared with if we don't consider hardware at all? The answer at least on this MNIST we test is not, because look at these two FPGAs. It doesn't matter, you look at the accuracy drop even from without any hardware constraint to the tightest timing constraint. This one, the accuracy loss is below 0.9%, right? And then we look at different data sets, from MNIST to ImageNet. We look at the results. It doesn't matter which network, which data set, or which task we're looking at. It's always the same. The accuracy loss is below 1%. And of course, the tighter the timing spec is, TS4 is the tightest timing spec. For example, 2 milliseconds. You get the highest loss in terms of accuracy because you have to prune more, right? More potential candidates become infeasible because of the violation in terms of timing. So you get, but even on TS4, even on ImageNet, the drop is below 1%. And in terms of the search time, the tighter the timing spec is, the faster you can run, and up to 10 times reduction in terms of the inference, in terms of the latency. Now, finally, this is all comparing with the NAS, right? What if now we want to look at how it compares with hardware-aware design, our co-design philosophy? Does it really help, right? So this is the results on CFAR10 and with the 7Z020 FPGA. We look at this is the hardware efficiency and also accuracy for the training and for the inference, right? So you can see that actually this is we call the Pareto frontier, which offers the best trade-off between accuracy and hardware efficiency. This is what we get from the hardware aware. Let's say we fixed a particular tiling, a particular set of tiling parameter, and they're never changed. We fixed a particular mapping, we fix a scheduling. So these are fixed, right? Once we fix them, then this become a hardware aware NAS. Now, once you do that, this is the Pareto frontier, and this is our Pareto frontier, where if you allow everything to be flexible, you don't fix the FPGA design, and there is a big improvement in this frontier by simultaneously exploring both design spaces. And then we also, these are in terms of the numbers, we compare our approach with, like I said, the hardware aware NAS. We also compared it with a sequential optimizer. Now, the sequential optimizer basically means, okay, let's start with a particular FPGA mapping. Then we find the best neural architecture for using the hardware aware. Now, once you find this optimal neural network for this particular FPGA design, then we redo the FPGA design for this particular neural network that we find, the neural architecture we find, right? You can run hardware optimization to see what's the best design for this particular architecture. So this is what we call the sequential optimization. And our co-exploration. We have two versions of it, two extreme versions of it. The first one only focuses on hardware efficiency. So we put a lot of weight on the hardware performance. And this one is we put a lot of weight on the software in terms of accuracy. We put a lot of emphasis on the accuracy. So as a result, well, we can look at it doesn't matter which one looking at. We get a smaller, much smaller number of parameters. We get an accuracy. Well, this one, the accuracy is lower than these because, again, we only focus on hardware, mostly on the hardware performance. You get almost 100% of pipeline efficiency. You get 35.5 frames per second, and this is energy efficiency, right? So you get you can get almost 100% of pipeline efficiency. And if we put most of the emphasis on the accuracy, you get higher accuracy than the baselines. Of course, the pipeline efficiency drops, but we can see that it doesn't matter which extreme end we end up with, we can get better in that particular metric of interest compared with the baselines. And of course, in most reality, real case, you are going to be in between, right? You won't go to the too extreme. The same thing for ImageNet. Basically, you can get a very high pipeline efficiency if you want to go for hardware performance. You can get a higher accuracy if you want to go for the accuracy, right? But for the software. And now to end this discussion, I want to show you one interesting result to further support the importance of co-exploration. The x-axis being the size of the model. All right. So let's say that if we have we know that, okay, the FPGA has limited capacity, right? And what if we, instead of doing this co-exploration, right? What if we just limit our search space because we know the FPGA? So we know approximately what's the maximum potential size of the neural network we can handle. So let's say we just put a limit on the size of this neural architecture we can sample, the RN can sample, and then we just do the regular nest without considering hardware at all because we already limit the size, so that will probably fit, right? So we tried that, we just limit the size to 150K in terms of the model size, and then we run the neural net architecture search without considering the hardware. So the actual result is that we find even if you just limit the model size to 150K, you look at there's a wide spread across all the models with the same number of the size. There is a wide difference between the hardware efficiency. It can go all the way down to close to 0% in terms of efficiency, all the way up to close to 100%. Well, this should be 100%, right? So there's a wide spread. So you cannot get the hardware performance or the hardware efficiency simply by restricting the size of the model. So you have to do something else. That's why you can't just limit the size of the model in the search space to take the hardware design into consideration. You have to actually design it or do some quick estimation of it in the optimization loop. So that's our very first work that I explained in detail, which I hope to give a brief idea of the philosophy and why I want to look at it, how we look at it, and what's the benefit we can get, right? And beyond that, we think, hey, there's nothing that can stop us from looking at other platforms that are programmable, right, or that can be changed. So in ICCAT 19, we tried the co-exploration of hardware design of the neural architecture and the quantization. So we further throw in the quantization. And then we further do the ASIC design, the simultaneous design of the ASIC, the accelerator, and the neural architecture. And then we expand to network on chip. We expand to computing in memory. We expand to secure inference. And most recently, we also did the quantum accelerator and neural architecture co-design that was published in Nature Communication, and we had a commissioned Nature article, Nature paper as well as in review. So I'll just again very quickly go through some of these works that are because they follow a very similar idea and philosophy. So I can go quickly. The first one that I mentioned, it's architecture, hardware, and quantization co-exploration. So that's because we think, in addition to making the network smaller, we can also try to use, people also sometimes do quantization, right? That's a very common strategy people use for the edge acceleration or edge deployment of neural networks. So you can see that even for a VGG16, some of the convolution layers are too big for the low-end FPGAs. So what we did is we did a similar framework. We just, in addition to the network, the hardware accelerator, the FPGA mapping, in addition to those schedule, we also throw in a different quantization, right? So basically, in the controller, in addition to those hyperparameters for the neural architecture, like the stride height, stride width, polling height, polling width, we also add a integer width of the weight and fractional width of the weight, and integer width of the activation, fractional width of the activation. So these are the hardware quantization hyperparameter that are being included in this reinforcement learning, right? So in addition to those parameters for the neural architecture. And as a result, I can show some of the results. So this is the target. This is what we know the capacity, the number of lookup tables for on the FPGA, the maximum number of lookup table we can use. And this being the maximum, the throughput target, like what's the throughput we wanted to achieve. Different designs. These batches are the ones identified by NAS, by the hardware, the FPGA, the code design, but without considering the quantization. And these are identified simultaneously considering the FPGA design, the neural architecture, and the quantization. So you can see that if you don't consider the quantization at all, after you find the neural architecture, right, even you simultaneously explore the FPGA design as well, there is a big drop in terms of the accuracy after you do the quantization. But if you do allow the quantization to be included in the search process, then there's only about 3% of reduction in the accuracy. And for both this design and this design, they have exact same design target. So we know it's a fair comparison. You can see that both can be quantized after quantization. You can both get same throughput.
I could not go through that part.
And I think someone. And then the parameter size is also reduced, right? So this is to show that it's actually also beneficial to include quantization into consideration in the search process as well. And similarly, we do this is also very interesting work. We simultaneously consider the ASIC accelerator design and the neural architecture search. Now, the challenge for the ASIC design is actually there are multiple fold. The first one being the ASIC really has a huge design space, right? You can build everything from scratch if you desire. It's not like an FPGA. More or less, you're just looking for the tiling parameter, the scheduling algorithm, right? That's it. These are, you can quantify them, but for an ASIC, there are just unlimited number of possibilities. So what we do is we we look at all the existing manual designs. We look at the ISCC, JSSC. We look at those design conferences, design journals. We look at how people design them, and now we look at there are a few different design styles that we borrow. For example, the 10电脑 style. There's NVDI style. Look at the different design styles, and we extract these styles as a template. We allow the hyperparameters in these design style to change, like the number of P's, the bandwidth. We allow them to change, but we fix the template. So this way, we can narrow down the design space to, you need to pick a template for your problem. Do you use a 10电脑 or a NVIDIA, or no, which one you use? And also, we can use a mixture of them as well if you need, right? The challenge number 2 would be there are multiple tasks in the application. Usually, if you build an ASIC accelerator, you don't build them just for one application. Usually it's for multiple, right? You want it to be able to run, for example, in autonomous driving. You want it to be able to do classification. You want it to do segmentation, and different tasks. So that's why we also include simultaneous search architecture. We search one architecture for each task. We want our accelerator design to be optimized simultaneously for multiple applications that will be run on this accelerator. And finally, how do we evaluate the performance of once you have an ASIC design, how do we evaluate the neural network performance on that accelerator design? Fortunately, we collaborate with Georgia Tech, and they have a Maestro framework that we can directly use to get a quick idea of the accuracy in terms of latency, in terms of energy efficiency of a neural architecture on a particular ASIC design. So this is the main flow. It's quite similar. Again, you can see from what we had before. You have basically we have a switch to control whether we are doing the architecture exploration or we are trying to optimize for the ASIC design within the same reinforcement learning framework. And if you want to go for the architecture exploration, you train it, you validate it, get the accuracy, and also you go for the cost model, the Maestro. It will do the mapping and the scheduling. It will give you the in terms of the performance as well, the hardware performance. Or you can also choose to just optimize the hardware because ASIC space is also pretty difficult to optimize. You can simply turn on this switch and just go for the optimization for the ASIC design. So this is the, again, we have a controller. The controller is, have a part of it that generates or controls the design of the hyperparameters in the ASIC, including the number of Ps, the bandwidth. There are also different parts of the controller deciding the neural architecture for different tasks. Again, ASIC accelerator are for multiple tasks. So we allow the controller to generate different networks for different accelerator, for different tasks. So to show you some of the results, let's say that we assume the workload to be one classification on CFAR, one segmentation on Nuclei. This is the design spec. So we want the latency to be no larger than 8 times 10 to the 5th cycles. The energy should be below 2 times 10 to the 9th, and the area is 4 times 10 to the 9th square micrometer. So this is our design spec. So anything has to be within this cube, right? It has to be lower than this point. And we tried a few different specs, the different design strategies. The first one being, hey, let's just use the minimum neural architecture, right? This one we can guarantee it'll fit. It'll fit on whatever accelerator. And we just focus on design of the accelerator to see what we can do. But if you use the minimum resource, if you use the minimum design, the accuracy and IOU is pretty low, right? As you can expect. And if we look at all the solutions actually sampled by the reinforcement learning engine, and they are scattered in the space, and finally we identify this is the optimal one. It gives you the highest accuracy for the two tasks. And as a comparison, we also compare our approach, the NASIC compared with a two baseline approach. One is using first just run the neural architecture search without any hardware awareness. Then we design the optimal ASIC accelerator for that architecture. So it's a sequential approach. Or we first use an existing ASIC accelerator design. We can run a hardware aware NAS for that particular design, right? The hardware design now is fixed. So either way, we can see that the results in terms of the latency, in terms of the energy efficiency, and in terms of the area, our approach can achieve the best. And similarly, we can also do the co-design of neural architecture and the network on chip, where the motivation being we try a neural network identified by NAS. We find that if you have a network on chip, a NOC, with 4 processing elements, Now, for one design, you use the bus interconnection. The other one use a 2D mesh network-on-chip architecture. Compared with the single processing element design, you can actually reduce the computation time, but sometimes the data transmission or the communication time will dominate. And because the communication time will dominate, how do we design the communication? It's something we can explore, right? So we look at that, and actually we compare two different routing algorithms for the communication XY routing. And if we can do some kind of flexible routing, we can change a little bit. Then you can see that this is the hardware awareness for a fixed XY routing. The throughput bottleneck is about 5.1 millisecond. And if you can do a flexible routing, you can simultaneously design the NOC routing and the neural architecture. You can reduce the communication to 3.5 millisecond, right? So that's a big reduction, about 30% of improvement. So the idea is the same. I'll skip all the details. Basically, we have two loops. One loop that identifies the neural architecture, another loop that identifies the network on chip design, including the partition, including the mapping, including the routing, that can give you the best routing and design of the NOC in pair with the neural architecture identify that gives the best accuracy and the speed. So here are some of the results. You can see that we actually show the process of our search, the co-exploration. This is our throughput bound, meaning that we do not allow the throughput to be below 0.5 gigabit per second. So anything on this side, a failed design. And our search process can be divided based on a hyperparameter in our search alpha. And again, I will skip detail, but this is the initial phase. In maybe you can just think of as maybe the first, a few thousand iterations. The next, the phase, and the final phase. This is where we finally stop. So you can see that initially, lots of the designs are inferior. They are not even infeasible, right? Most of the designs are here being explored. And then as we move into the later phases of the reinforcement learning, more architectures are being explored in the higher throughput range. And eventually, when we are almost ready to converge, most of the designs being explored are in the high throughput range right here, above 1.5, well above this throughput bound of 0.5. So you can see that it actually learns to push the to move towards the higher throughput range, right? Finally, I'll just show this is our final piece of the co-exploration. We look at the network, we look at the computing memory accelerator, and we figure out that there are lots of different network, computing memory designs. They use different devices. For example, the ReRAM, the FE-FAT, the FARA-FAT, right, the STT-MRAM. And each different device has its own unique characteristic. It has its own variation model. It has its own reliability, has its own power efficiency, right? Now, if you have a task that you want to accelerate, and let's say I know I want to use computing memory, but how, right? The first question, number one, what device you want to use? Question number two, what's the circuit you want to design, right? What kind of mesh do you want to use? Or what kind of array? What's the size of the array, right? And then, of course, you have to decide the data flow. This is similar to the ASIC. What kind of data flow do you want to use, right? And also quantization, because for computing memory, the data has to be quantized. So how do you do the quantization? So I asked my student, hey, let's just do a holistic co-exploration from device all the way up to circuit architecture, everything. Let's try to see if we can co-exploration. We can co-explore. The answer is yes. This is the, if we only consider quantization, but nothing else. This one is if we consider the noise, because we know the device, these emerging device has noise, and hardware awareness. Let's say we consider, hey, let's say we consider maybe, let's say we decide we use this one. We decide to use maybe the NOC circuit, or we decide to use this flow. Let's fix this. Then we can run a hardware aware design. And finally, our approach one with most emphasis on hardware, one with most emphasis on software performance. So that, again, two extreme cases of our framework. So you can see that, again, if you focus on hardware, you can get the smallest area, you can get the highest energy delay product, right? Although the accuracy, it's still comparable with the hardware aware one. And if you focus on software, you get a much higher, 3% higher accuracy. You know, of course, you also get a smaller area, even though it's bigger than this one, but it's still smaller than the baseline. So it's a very efficient framework as well. So you can see that most of our explored solution are in this area. If you look at hardware efficiency and error, well, if the process, you know, if you do a hardware aware one, they are in the region with, well, with the higher efficiency, with lower efficiency, well, this means higher. So this is a lower efficiency and worse compared with what identified by our approach. So finally, we go beyond hardware a little bit and we'll look at a co-exploration of neural architecture and secure inference. That's because we're working on medical image analysis. And for that, one critical need is to protect the privacy and security of the patient image. So usually what people do is they put everything on the cloud for the inference, but the image has to be encrypted before sending to the cloud. So for example, the image, this is the original image, CT, you encrypt it, send it to the homomorphic encryption convolution to do it in the cloud. And once you get the results, you send it back, decrypt it, you get the feature map. And then that's how you do the convolution. We call it homomorphic encryption convolution. You can do ReLU, but that requires a Gabler circuit to do the ReLU, which I'll skip detail, right? And then you can go do homomorphic encryption FC layers. That's how we do it. We do interaction layer by layer. And as you can see, this kind of framework, if you do Gabler circuit and homomorphic encryption, it's computationally very expensive. Number two, it takes a lot of bandwidth because you have to talk with the server back and forth in order to get the inference done, right? So again, this is done on the client with privacy. This is on the server on the public domain. And we think there is a way we can identify this best neural network run on the server with consideration of the potential communication and also this garbled circuit, so that the overall communication and the computation can be minimized. And we know it's a similar idea. We just, in addition to the accuracy, we add a performance evaluator by looking at the potential parameter for this homomorphic encryption, decryption, for the communication bandwidth, for the garbled circuit hyperparameter. So these are the things I will not go into too much detail. That these are the hyperparameters, the design results. But you look at the accuracy, the best architecture identified by our results, by our framework, can get a higher accuracy, can get about half of the bandwidth. You only need half of the bandwidth for the communication. And in terms of the time to do the encryption and decryption, we can also reduce it by at least 2 times. But at the same time, we'll get a higher accuracy. So that's the benefit for co-exploration of the secure interface and the neural architecture. So in conclusion, again, the main philosophy or the direction we'll be looking at in the past, for 3 or 4 years, is to simultaneously design the neural architecture and whatever particular accelerator or interface you need, so that we can try to deploy the AI to different platforms with the specific need. And finally, again, in the interest of time, I don't have too much time to go into every detail, but I've listed all the related references of our work on this kind of line of topic. So if you are interested, feel free to check out these papers or send me an email afterwards, and I'm happy to send you some of our references. So that's all. Thank you, and I'm open to any question if you have.
Thank you, Yiyu. Very interesting work. And any questions from the audience? So you are free to unmute yourself to ask a question.
Hello, Yiyu. This is Jiafan.
Hi.
I am a former PhD student of Texas A&M University. I have a quick question about page 32.
Okay, just give me 1 second. Let me go to how do I 32. Okay, go ahead. Okay.
Yeah, so in this slides, there are 5 steps, right? A, B, C, D, E. So my question is, are these steps happened in sequence, or they are just 5 different aspects of the process?
There are 5 different aspects. So they're not really they're not really, I would not call it in happening in like in a sequential order. I'm just putting this way to show it's a bottom up kind of layers. You go from device layer all the way up to the neural architecture layer. But essentially what we did they are all converted to hyperparameters in the reinforcement learning search framework. So you sample a circuit, for example, you sample device sampling, you decide which device you use. That's a decision. And then you sample a circuit topology and the hyperparameter, the size of the layer, the size of the array. You pick one data flow, you pick one quantization the you know how many bits you use, and then once you have that, you get a hardware performance, and that can be used to guide the you know to compute the reward or penalty for the reinforcement learning.
Okay, so then keep on doing this kind of things to finally improve the performance.
The ultimate goal are 2. There are 2, and we use a weighted sum for these 2. Now, one is the accuracy. We call it a software objective. And accuracy, of course, in terms of the device variation. So because you have these devices that are, you know, they have variations. So the average accuracy with the device variation. And then we have a hardware metric in terms of depending on what you're looking at, area or speed or energy delay product. And I think in this work, we tried a combination of these. But so these are the things we compute, and then we add them in as we'll get the results as a reward or penalty.
I see. Okay. Thanks. Yeah, that's it. Thank you.
Other questions from the audience? So you actually, I have several questions.
Okay, sure.
Yeah. So the first one is that so it looks like so the MNIST engine used is based on the reinforcement learning, right?
Yes. Yes.
Have you ever considered about use some other like the differential something like that?
Yes, we did. And in fact, we explored for quite a while. Shall we use darts or reinforcement learning for this kind of? As you can see, you know, by the time we actually did these works, there are darts already available. The reason we did not use darts is if you wanted to actually put hardware constraint or the specification into the framework. So let's say, hey, I don't want my latency to be above 2 milliseconds. For that of constraint, the hardware constraint, it's almost impossible to make it differentiable. There are ways you can approximately differentiate the latency or maybe energy. There are approximations. But if you do that, even if we do that, we differentiate these hardware constraints. There is no way you can use them as a bound. So for example, I can simultaneously I can add a weight to simultaneously, usually would minimize the weighted sum of my accuracy and my latency. That's fine. There are potential ways to go around, but that can handle. But if you say, hey, I want to maximize my accuracy and I want my latency to be below 2 milliseconds, then Dart is not capable of doing that. So that's one reason. And the second reason is, in fact, our frameworks, the main advantage of Darts is that they are fast. They're much faster than the reinforcement learning-based framework. But on the other hand, we find that with our hardware pruning, because we have the constraint, we know that many of the sampled architecture, they're just not feasible. They just take too long, they're too large, too big, taking too much of an area. So we don't even have to train them. So the actual search time of our network, of our framework, they aren't too bad. They're pretty okay. So even for ImageNet, they just take just a couple of hours to do. So that's why we decide to go with the reinforcement learning. So the benefits of Darts are not quite obvious in our case.
Yeah, that make perfect sense. Yeah, because you can quickly prune many unsatisfied choice at the very beginning of the training.
Yep.
And another question. So I remember you have one slide that you have some very important observations. So given the fixed model size, so you mentioned that just to reduce the model size net is not enough because the hardware efficiency may be quite different. I remember you have some figure about that. Oh, can you hear me?
Yeah, I can hear this one, right?
Not this one, I think this one. Yeah, this one. And okay. So I was wondering, so how about the such the similar relationship between the hardware efficiency and the flops? Because I think in many cases that so the at least for the accuracy, so the computational cost is also very important.
Yes. So there is a higher correlation between the flops and between the flops and the model size. There is that correlation is higher, and if you are only interested in the but even though the range, the potential variation becomes smaller, there is still a pretty big variation so even your fixed data, you are still not able to identify the best architecture. So it's smaller than this, but it's still big in terms of flops.
Okay, thank you. And that's all my questions. So other questions from the audience?
Yeah, if you think of any question after this after my talk, feel free to shoot me an email. I'll be happy to initiate some discussion over the email as well.
Okay, thank you, Yiyu. So this is a very informative and excellent talk. So also thank everyone to attend this week's talk. So see you next week.
Thank you. Bye-bye.
Thank you. Bye.